Let's look at the simple electrolysis of electrolyte solutions. A seemingly simple experiment, but with lots to consider. These days the examination boards limit the solutions that the students need to know about. They are usually hydrochloric acid, sodium chloride and copper sulfate solutions. The complexity in teaching comes about because water provides competition ions in the electrolytic solutions as water ionizes to H plus and OH minus ions. Therefore there are competing positive ions at the negative electrode and competing negative ions at the positive electrode. Whether you call the electrodes anodes and cathodes will depend on your exam board specifications. The equipment you may wish to use to demonstrate electrolysis will depend on whether you need the students to see that current can flow through a solution of an electrolyte, or whether you wish to collect the products of electrolysis at each electrode. In the simple case, graphite electrodes are held in a solution of the electrolyte and are connected up either to a bulb or an ammeter and of course a 12-volt DC power source. In the circuit we have here, we have both a bulb and an ammeter in series. One or the other should be enough to indicate that a current is flowing due to the movement of charge through the solution. The movement of charge here, of course, is the movement of ions. Electrolysis practicals, whether as a demonstration or for student use, can be problematic. Your power source may have fuses that blow, which will need replacing, or there may be a trip switch to which the students are unfamiliar. They can be breakages in the wires that the students use, or that the teacher is using in their demonstrations. Ideally, the crock clips that are being used are not corroded. Corrosion, of course, is an insulator. Probably the biggest challenge using graphite electrodes is to tell whether or not there's a break in the graphite electrode within the rubber itself. If there's a break in the electrode, there's not a completed circuit. I suggest that before any electrolysis demonstrations are used, the equipment is first checked. Showing the students how you do a check on the equipment is a valuable learning aid for them anyway. When you put the electrodes into the solution, ensure they don't touch and ensure they're not too far apart from each other. In sodium chloride solution, it's the hydrogen ions that discharge, not the sodium ions. Hydrogen being a positive ion will discharge at the negative electrode. And in a simple apparatus, this is hard to demonstrate that you're producing hydrogen. However, at the positive electrode, it's the chloride ions that discharge in preference to the hydroxide ions, so chlorine gas is formed, which, apart from being able to detect with your nose, will bleach damp indicator paper white. That is if you're using blue litmus paper. If you're using blue litmus paper, you'll notice it will go pink first before it goes white. This is because the chlorine in the solution forms a mixture of hydrochloric and hydrochlorous acids. The chlorine in the bleach is then going to bleach the pink indicator paper white. If you pass a current through that solution for a while, you will notice the solution becomes more alkaline, which you can test for with the relevant indicator paper or pH probe. It's because effectively you're removing hydrogen ions from the solution, therefore displacing the equilibrium towards the hydroxide ion. The electrolysis of brine or saltwater solution leads to the formation of sodium hydroxide in the industrial process. Hydrochloric acid electrolysis will give the same products as sodium chloride. The electrolysis of copper sulfate solution liberates oxygen at the anode, again difficult to test for in this apparatus, and copper is deposited at the cathode or negative electrode. Pure copper is pinkish in colour rather than orange. This is a surprise for most people. The copper will coat the electrode and cause copper as a precipitate within the solution, and so the beautiful blue colour of copper sulfate solution darkens. If you let the current flow for several minutes, sufficient copper can form at the bottom of the beaker to short circuit the electrolysis cell, causing the solution to heat up. Commercial electrolysis cells are available and can be used to collect the gases formed at the negative and positive electrodes. Setting this up is quite a fiddly procedure, as the electrolyte needs to be present in the small ignition tubes before they're placed over the electrodes. To do this, the electrolytic cell needs to be full, and you need to use your little finger. With the ignition tube full and using your little finger, place the ignition tube over the electrode. Take out some of the solution when both electrodes are covered Otherwise the displaced electrolytic solution would have nowhere to go. The design of these commercial electrolytic cells ensures that you can't get a short circuit by touching the crock clips together at the electrodes. Homemade versions of this apparatus can be made using cut down Coke bottles and graphite rods, the sort that kite makers use as strengtheners as the electrodes. As the bottles are actually wider than the commercial electrolytic cells, it's easier to place the ignition tubes over the electrodes. Testing for oxygen in an ignition tube is quite tricky. One top tip: split your spill lengthwise. It is possible to use electrolysis to discuss oxidation and reduction, but this for most students is probably a step too far. However, the liquid in the tube could put the glowing spill out, and there's not a great deal of oxygen there anyway to perform the test.